Awesome. All right. My name is Gabrie Hempel. This is Hacking Humans, Addressing Vulnerabilities in the Advancing Medical Device Landscape. So the first question is usually, how did I end up here? A couple weird things happened to kind of bring this intersection of medical and cybersecurity to life. So weird thing number one, I studied neuroscience and psychology in undergrad, worked in neurobiology for a while, and then worked in pharma after graduating. And I worked with a lot of medical devices and a lot of just patient-specific things, and kind of fell down that InfoSec rabbit hole once I started working with medical devices because I wanted to figure out why they were so vulnerable. So first, let's talk about connected devices. The Internet of Things is comprised of devices that possess internet connectivity, sensors, electronics, etc., and that use the internet to communicate and interact with other devices. Most of the times, these devices can be remotely monitored and controlled. They can be segmented with a variety of categories, including consumer, commercial, and industrial applications. Consumer applications are created for consumer use and can include connected vehicles, smart home devices, wearable technology, i.e. Fitbits or Apple Watches, connected healthcare technology, which we'll be discussing here, and appliances that have remote monitoring capabilities. Commercial applications are also comprised largely of medical devices. These devices are generally used for data collection, remote health monitoring, and emergency notification. Can also include transportation system controls, vehicle-to-everything communication, and building and home automation. Finally, industrial applications of IoT devices can include manufacturing devices, especially control systems, and agricultural devices. I had to include Patrick, so. All right, so now let's talk the Internet of Medical Things. It's basically IoT, but make it healthcare. Internet of Medical Things is a connected system of medical devices and apps that collect medical data that is then provided to information systems through networks. A lot of times, these devices enable remote health monitoring and emergency notification, and can range from heart rate monitors and internal defibrillator implants, aka items used directly on a person, or smart beds and diagnostic machines, which are items used to aid a patient's care. So why the fuss over medical devices and their connectivity? They have become such an integral part of our healthcare tech landscape that the numbers are pretty staggering. 6.7 million people in the United States each year, on average, receive implantable medical devices. Aside from that, hospitals tend to have 10 to 15 connected devices per bed in their facilities. The problem with this is that devices boast the latest smart technology and enable connectivity with other devices. However, this generally leaves them vulnerable to threats, and people are starting to notice and exploit that. Medical device recalls increased 126% just in the first quarter of 2018, and a lot of these recalls were due to security vulnerabilities and threats. Most of the weaknesses were discovered by government entities and academic institutions. The FDA is just now beginning to release preliminary guidance to both assess impact and establish regulations for these devices. Let's dive in a little bit deeper and discuss how vulnerabilities in medical devices range from rudimentary to advanced, how this can endanger both patient information and safety, and how we can devise a more rigid system to diminish the threat of the attacks. First things first, why should we even use these devices if they're so vulnerable? According to Goldman Sachs, connected medical devices save the U.S. on average $300 billion in healthcare per year. They increase revenue and decrease costs, which is ideal, and provide access to better and new types of information that a patient either may not have had access to previously or hadn't had a way to measure. This, in turn, leads to more accurate underwriting and new pricing models for consumers. The devices will also help improve the quality of life for many of the patients that use them. Remote monitoring is made possible by connected medical devices and allows healthcare providers to capture patient data instantaneously, as well as allow the patient to live their life more normally than they previously may have been able to. So first, let's talk about implantable devices. This is the Medtronic CareLink 2090, which is the software for an internal defibrillator. This works similarly to a pacemaker. The manufacturers had a software deployment network that allowed for the download of new software directly to the pacemaker. However, security researchers found vulnerabilities in which an individual could pretty easily update the programmer with a third-party software. The FDA issued a bulletin disabling the SDN and requiring manual updates until the vulnerability could be fixed. The vulnerability was discovered and publicized by Billy Rios and Jonathan Butts from Whitescope, LLC. They uncovered a chain of vulnerabilities in Medtronic's infrastructure that an attacker could exploit to control implanted pacemakers remotely, deliver shocks patients don't need or withhold ones they do, and essentially cause real harm. In essence, the 2090 uses a VPN to securely download its updates, but doesn't verify that it's still connected to the VPN before downloading the updates. The device will establish an encapsulated IP-based VPN connection to a Medtronic-hosted update network. Once established, it makes a request to an HTTP non-TLS server across the VPN, which responds and provides the updates. However, the programmer-side service responsible for this HTTP request doesn't check to make sure it's still connected to the VPN before actually making the request. This could be exploited if an attacker terminated the VPN and intercepted the HTTP request and responded with malicious updates via a man-in-the-middle attack. Medtronic disabled the network-based software update mechanism, including the VPN and HTTP subservices. Users were instructed to obtain and apply updates via controlled USB devices. It was also recommended that users minimize network exposure for all control system devices and ensure that they were not accessible from the internet. Next, we have infusion pumps, which are used to deliver medicine in controlled doses in hospital settings. We're specifically going to talk about the Smiths Medical MedFusion wireless infusion pump, but similar vulnerabilities have been found in nearly identical devices. It was discovered that remote attackers could gain access to both the communication and therapeutic modules. There were various attack vectors: easy buffer overflows due to a lack of verification of input buffer size, hard-coded credentials, improper access controls, and improper certificate validation. Scott Gayu, a security researcher, identified a handful of vulnerabilities in this MedFusion infusion pump. In short, the pumps are used to deliver small doses of medication in acute care settings. A third-party component in this pump did not verify the buffer input size prior to copying, leading to a buffer overflow and allowing remote code execution on the target device. While a difficult exploitation, it was potentially extremely malicious. A third-party component used in the pump read the memory out of bounds, which caused the communication module to crash. The pump, which left with its default network configuration, used hard-coded credentials to establish a wireless connection automatically, even if Ethernet was connected and active. We also see improper access control on the device. The FTP server on the pump doesn't require authentication. The server also contains hard-coded credentials, which are not fully initialized. Telnet on the pump also used hard-coded credentials, which could be exploited if the pump was configured to allow external communications. The infusion pumps did not validate the host certificate, which left it vulnerable to a man-in-the-middle attack. And then my favorite, the infusion pump stored some passwords in the configuration file, which are easily accessible if the pump was configured to allow external communications. Smiths released updates to mitigate these vulnerabilities, but also suggested that users applied defensive measures. These include assigning static IP addresses to the pump, monitoring network activity for rogue DNS and DHCP servers, ensuring network segments are segmented from other hospital and medical technology infrastructure, using VLANs, practicing password hygiene, and performing routine evaluations. So in general, there's many connected devices within hospitals. These include imaging systems like ultrasound machines, MRI, PET, CT scans, and X-ray machines, treatment equipment like infusion pumps, lasers, and surgical machinery, life-supporting devices like ventilators, anesthetic equipment, and dialysis machines, and medical monitors like O2, blood pressure, ECG, and EEG machines. Most of these don't have any sort of inherent antivirus in place, which poses a problem. This can allow malware to spread quickly between connected devices. So with all these dangers, why are connected hospitals and medical devices a good thing? Connected devices, like the ones mentioned previously, substantially reduce the amount of time it takes to read and record vitals and other information. Each patient in the hospital has, on average, 3 to 6 medical monitoring devices attached to them. So what kinds of incidents are plaguing hospitals and medical systems? 2018 was a record-breaking year for data breaches in healthcare alone. Since October 2009, there has been disclosure of almost 195 million healthcare records. This equates to affecting 59.8% of the United States population. So what are our solutions to these vulnerabilities? The FDA has issued guidance, both pre- and post-market, to offer recommendations for management of medical device security risks. MITRE unveiled a medical device security playbook in October 2018. This enables healthcare organizations to plan for and respond to incidents and develop a preparedness and response framework. The FDA is also leveraging the NIST cybersecurity framework. It's composed of 5 core functions: identify, protect, detect, respond, and recover. They also have been assembling information sharing analysis organizations and holding forums. And finally, they've been partnering with the Department of Homeland Security in order to mitigate wider attacks. So first, let's talk about the FDA-issued guidance. The agency developed this guidance as a result of an executive order that was aimed at strengthening national security, economic stability, and public health and safety. This guidance is generally for medical device manufacturers and applies to any marketed and distributed medical device, including devices that contain software and firmware or programmable logic, devices or software that is a medical device, including mobile medical apps, medical devices that are part of an interoperable system, and legacy devices, aka devices that are already approved, on the market, and in use. So the FDA guidance outlines a common vulnerability scoring system, which provides numerical ratings corresponding to high, medium, and low by assessing a number of factors, including the following: attack vectors and whether they're physical, local, adjacent, network, etc. The complexity of the attack, whether it's high or low, whether privileges are required to complete the attack, and whether user interaction is even required, the scope of the vulnerability, the impact that an exploit might have on confidentiality, integrity, and availability of data, the exploit code maturity, whether it's high, functional, proof of concept, or unproven, the remediation level, whether unavailable, a workaround, a temporary fix, an official fix, or something undefined, and finally, the confidence in the report. These factors are weighted and aggregated into one of the scores on the vulnerability scoring system. Once the vulnerability exploit is rated, there's another side to the investigation. Because these devices are used on and for humans, we need to assess the severity of patient harm. The FDA provides a scale of 5 categories to assess patient harm. We start with negligible, which is just an inconvenience or temporary discomfort for the patient. Minor, which might result in temporary injury or impairment but does not require medical intervention. Serious, which results in injury or impairment requiring professional medical intervention. Critical, which results in permanent impairment or life-threatening injury. And catastrophic, which results in patient death. It's also necessary to evaluate the risk of patient harm in medical device breaches or exploits. We need to determine whether the risk of patient harm is controlled, which is acceptable, or uncontrolled, which is unacceptable. Oftentimes, this is done by assessing a matrix with a combination of exploitability and severity of patient harm. A binary determination is recommended by the FDA, i.e. one or the other, with no gray areas. Controlled risk is present when there's sufficiently low or acceptable risk of patient harm due to the vulnerability. Manufacturers are asked to perform device enhancements that will strengthen security, deploy controls for a defense in-depth strategy, perform routine updates and patching, and submit an annual report to the FDA if they're under pre-market approval. An example of controlled risk could be as follows. A manufacturer received a complaint that a gas blood analyzer has been infected with malware, and it's unknown as to whether the malware could alter data on the device. Once investigated, the presence of malware is confirmed. However, the malware doesn't result in the manipulation of unencrypted data stored and running through the device. The device's safety and performance is not impacted by the malware, and the manufacturer determines that the risk of patient harm is a controlled risk. Uncontrolled risk is present when there's an unacceptable residual risk of patient harm due to insufficient risk mitigations and compensating controls. Manufacturers should consider exploitability of the vulnerability and severity of patient harm if exploitation is carried out. Manufacturers are also asked to remediate uncontrolled risks as quickly as possible and to report them to the FDA. An example of uncontrolled risk could be as follows. A hospital submits a report that a patient was harmed after a medical device failed to perform as intended. Upon investigation, it was determined that the medical device malfunctioned as a result of exploitation of a previously unknown vulnerability in the software. The outcome of the investigation and impact assessment determines that the exploit impacts the device's safety and essential performance and could have contributed to the patient's death. A report is filed in accordance with the reporting requirements, and the manufacturer notified its customers and develops a validated emergency patch to remediate the issue. Now for part 2, the MITRE playbook. MITRE, which I'm sure you've heard of, found after some research that after a breach, healthcare providers didn't really know with whom to communicate, what actions they were supposed to take, and what resources were available to them. The MITRE team worked with the FDA to identify stakeholders and develop a plan for preparedness and incident response. The first phase MITRE wants us to consider is preparedness. Secure design of medical devices in question is a huge concern, especially identifying and securing any third-party components that might be part of the device, and providing service layer access during an incident in order to ensure minimal disruption of clinical ops and a more rapid response. Doing an asset inventory and knowing what is connected to the network is also a big part of preparedness. By maintaining a baseline set of information about each medical device, the baseline set of information will better be able to provide an account for and manage devices before, during, and after an incident. Hazard vulnerability analysis is used to assess and identify potential gaps in emergency planning as well. Therefore, an emergency ops plan is also necessary to describe how a provider will respond to and recover from a threat, hazard, or other incident. Building upon this, communication is key during an incident. An incident response communications plan will help with all aspects of communication during the incident, especially with incident sharing, knowing how incident sensitivities can be shared, incident identification, incident notification, or how outreach is initiated, situational awareness, and communication templates to streamline the process. Finally, user awareness training is important in preparedness for a security incident, especially in terms of classification and identification. The next phase of the MITRE playbook is detection and analysis. The first part of incident detection and analysis is identifying or establishing that an incident has occurred. Is it an actual incident? Next, we must categorize and prioritize the incident. This is where those charts and scales come in, so we know how severe an incident is and whether it impacts patient safety or not. Once we know the scope of the incident, we have to report. Oftentimes, there are formal and informal reporting obligations that accompany discovery of an incident. Analysis will be done once the initial incident parameters have been established in order to provide insights on both the vulnerability and the impact within the healthcare organization. Finally, documentation will be carried out. Phase 3 of the MITRE playbook is containment, eradication, and recovery. Once an incident is confirmed, response begins. Oftentimes, a healthcare organization will use a contain, clean, and deny strategy, and then monitor and record when cybersecurity criminal activity is suspected. It's important for organizations to perform effective containment and minimize impact on healthcare delivery in other areas of the organization. Finally, phase 4 is the post-activity phase. Here we assess lessons learned and conduct hot wash sessions to elicit feedback on future responses. We will also engage a forensics investigation at this point and make any plan updates we feel necessary for the future. MITRE and the FDA came together to streamline and standardize the playbook and the post-market guidance. They forged a partnership so that MITRE could provide the FDA with strategic and technical support. They also leveraged MITRE's expertise across multiple federally funded research and development centers and independent research in the areas of cyber and homeland security. Both groups leveraged the NIST framework in order to create their plans, with the hopes that the healthcare groups and device manufacturers will be well positioned to manage those incidents through planning and practice, along with the support and collaboration of manufacturers and regional and national partners. So the difference in responsibility between these device manufacturers and a healthcare organization that might experience an event firsthand are: device manufacturers need to protect their intellectual property through server hardening and authentication, secure devices through code signing, secure boot, and platform hardening, protect critical data through messaging certs, encryption, and MPKI, and protect their manufacturing integrity through platform hardening and authentication. Healthcare organizations, by contrast, need to manage their contracts and requirements, perform holistic asset reviews and asset management, manage and mitigate risk, and detect anomalies in network security and security gateways. Both need to come together to ensure secure communication and access through authentication and access management. So the key takeaways of this presentation are as follows. Medical device technology is progressing faster than research on vulnerabilities for these devices. We need to begin to develop and implement a concrete plan for mitigation of risks to both patients and information in the healthcare system. And the FDA and MITRE guidance is a step in the right direction toward a universal program for leveraging these risks. Thank you.